Awesome. But yeah, so what we have today, so this is the second seminar in our Infusion Seminar Series. So our speaker today is Sheldon Fernandez. He graduated from computer engineering here at University of Waterloo in 2001. And so he currently serves as the Vice President of Engineering at Infusion, where he specializes in developing reusable solutions and intellectual property within the organization. So this talk today is actually on, it's an introduction to quantum computing, so it should be some pretty interesting stuff. So let's give a warm welcome to Sheldon now, okay?
Okay guys, thanks for coming to class. I always when I start lecturing at Waterloo, I thank you guys for coming to class because I had the worst attendance record in the history of EC, I think. So we're going to be talking today about actually a fun thing, I hope. It's exploratory. It's something that you probably won't have encountered in a practical way, and that's quantum computing. Last night, actually, I was going through the slides, and I originally developed this presentation for engineers who are already working, so engineers who have been through formal schooling and undergrad and masters, and I was trying to think about some of the concepts we cover here and when you guys learn them. And so I actually was on the EC website yesterday and I was trying to remember my courses, and in fact some of what we're going to talk about will foreshadow what you'll learn in 209, which I think you take in 2A, which is I think the electronic properties of materials, and then 231, which is like the device physics for like semiconductors and stuff. So we're going to cover some of that, but in a very broad way, and we're going to look at this exciting new area called quantum computing. Okay, so we're going to look at some theoretical foundations. We're going to talk about, some of the principles of quantum mechanics that make quantum computing possible. We'll look at something with respect to quantum algorithms. These are algorithms that can only be run on a quantum computer and not a classical computer. And so you'll see some of the innovations that quantum computing brings to the field. Then we'll take a look at some applications. So what are some of the practical effects of quantum computers? How might they change the industry? And finally, we'll talk about, how far are we away from real, tangible quantum computers? We'll take a look at the current progress in the industry. Okay? So let me start off by asking you guys a rudimentary question, actually. And it's amazing how many engineers I asked at my work, and they all struggled with the answer to this. So let me ask it to you guys, and that is this. At the most fundamental level, at the most kind of essential, rudimentary, fundamental level, what is a computer doing? What is the most basic operation that we have with a computing device? Okay? Don't say email like my sister did, because that really doesn't make a lot of sense. You guys are first years. What is a computer doing at its most fundamental level? Any guesses? Yeah? Okay, so bit manipulation, adding bits and comparing them. Okay, anybody else? Anybody else want to take a crack? Is that the lowest we can go, the manipulation of bits and the adding of bits? Yeah?
Counting.
Counting what? That's a little bit higher, right? Okay, you're very close. At its most fundamental level, what a computer is doing is storing and manipulating on-off states. So bits, correct. And actually, it's quite remarkable. If you go and read Alan Turing's paper from 1938, I believe, where he first envisioned a computer, right? It's worth reading, actually, sometime, just historically, to find out where we're coming from. What he envisioned was this electronic device that would work off electronic impulses. Right, so what you'll learn in your subsequent courses is that really a computer, when you break it down to the lowest level, is just manipulating on-off states. Okay, and everything else is an abstraction from that. The adding of bits, the counting of bits, gates, and gates, not gates, and so forth. And so if we take a look at the history of computers, you'll see that the devices that have been used to manipulate on-off states have changed over time. The very first computers were what we call vacuum tubes. And these were tubes that didn't contain any air. The air had been sucked out, hence the term vacuum. And they had kind of a magnetic device within that, and it would basically flip current. And based on that, we would be able to store on-off states within a computer. The problem with vacuum devices or vacuum tubes was that they were very error prone. They were very clunky. You know, they weren't very efficient. How many people here saw The Imitation Game, the movie? Right? What Alan Turing is constructing in that is based on vacuum tubes, basically. And so they were the very first computers. And the second generation occurred with the invention of the transistor, something you will learn in 231. Does anyone know who invented the transistor and when it was invented? Probably the most fundamental invention with respect to electronic computers as we know it today. Anybody? There was a guy named William Shockley with two other people, and he was at Bell Laboratories, and they invented it in 1947 and 1948. They won the Nobel Prize in Physics in 1956, I believe, for that invention. And what you have in your laptops today are variations on that transistor. Okay, something called Mosfets, which are the most popular type of transistors. You know, these are metal oxide semiconductors. The third generation was basically the integrated circuit. So this was the idea that we could take transistors and put them on silicon substrates. And so that was done by somebody at Texas Instruments in 1956. And then we had the microprocessor. Okay, does anybody know what the first microprocessor in the world was? Okay, it was Intel, and it was called the 4004, and it was made in 1971. And the idea behind the microprocessor was that we would take the various components of a computer, the CPU, the memory, and put them on one single device, and therefore make it faster. So the question that is being prompted now is, what is the next innovation? What is the next thing that is going to radically change the face of computing? And the reason this is important is because at the current rates that we are working with respect to transistors, okay, so you can see here, over time, the power of computing gets increasingly more powerful, right? Or the power of computers, rather. And you guys probably have heard of Moore's Law, right? Which states that every 18 months approximately, the power of computers doubles. And you can see a graph here, which basically shows the number of transistors that they are able to get on a device. And what is interesting is that if you follow this curve, and you take a look at where technology is now. So, per the slide above, Intel have made transistors, 14 nanometers, which is incredibly small. IBM actually just last week announced that they've done an experimental one that's 7 nanometers. Eventually, this is going to break down. Eventually, the heat to size ratio of what we are talking about will collapse, and this technology will no longer be viable. So something eventually will have to replace these techniques if we expect to keep Moore's Law. That is, if we expect to see a linear increase in the power of computers over time. Another problem, when you get down to very small scales, which we are approaching with silicon-based machines, is something called quantum tunneling or electron tunneling. Does anybody here know what that is? Yeah?
So it's when electrons will jump to a theoretical position and be able to, but they will be able to the probability.
Very good, right? So it's when electrons will jump over a boundary, and you will learn this in 209. Okay, so one of the things you will learn is that when we get down to the quantum level, when we talk about quantum mechanics, and you'll see this on subsequent slides, we don't know the position of an electron. If you think back to high school, where you had this nice kind of quixotic, view of an electron circling an atom, and everything was predictable, the Newtonian world that they presented in high school, what actually happens is a lot more complex. And an electron is described by a probability wave where it could be in a number of locations. What you will learn in 209 is that at very small scales, if you bring an electron close to a medium, it can jump literally over that medium. And that is called electron tunneling. Now, this is used for practical purposes. We see this in fusion in the sun. There's something called electron microscopy, which basically uses this to get resolution at very, very small scales. If you go on the internet, you can actually see IBM, believe, were the first company to actually get pictures of atoms. And they did this using electron tunneling. The problem is, at this small scale, electron tunneling will produce negative effects in electronic machines, and therefore we'll have to come up with another technique to deal with the very small scale. Okay? One thing to appreciate is, and you will hear this a lot with respect to quantum mechanics and the quantum world, is that the quantum world is weird. Weird meaning the reality works in a way that we wouldn't expect to work in everyday life. So, there's one author who wrote, space-time ceases to be smooth at very small scales. It is not flat even in the absence of mass, but constitutes a turbulent quantum foam that results in tangible levels of weirdness. Okay, what did he mean by weirdness? Really, when we were talking about weirdness at the quantum scale, we were talking about two things that we will examine in a moment, and that is something called superposition and entanglement. These are the two principles of quantum mechanics which allow and facilitate quantum computing. Okay, so what is quantum computing at a high level? It is basically a computing device which works on the laws, based on the laws of quantum mechanics. And there are two benefits to this approach. The first one is instead of switching, instead of doing the storage of bits with transistors, imagine if we could do them with quantum particles, right? So imagine instead of having an on-off switch with the transistor, which is now very, very small, you could actually do it with like an electron or an atom. Imagine what that would mean for speed and power and the amount of information that you could store, in a given square footage or square nanometer. So that's kind of the first draw of quantum computing. But actually, the second, more important aspect of quantum computing is that quantum machines can take advantage of this weirdness that we do not see in the classical world. Okay, they can do things with algorithms and so forth that you would not expect to do, or you couldn't do if you had a classical machine, and we'll see that in a moment. Okay, so let's talk about some of the theoretical foundations. Let's talk about some of the theory of quantum mechanics that makes this possible. And the first thing is called superposition. Okay, superposition basically means, and this is strange, that a quantum particle can be in a state of flux. Okay, when we talk about the location of a particle in the quantum world, and this is something Einstein really struggled with, incidentally, is that we do not know where a quantum particle will be. The best we can do is describe it probabilistically. Okay, we can have somewhat of a bell curve that says the quantum particle can be somewhere in this location. It is in fact a superposition of all the places it could be. And what we'll see is that at the quantum world, at the quantum level, the minute you measure or attempt to measure the location of a quantum particle, it collapses and falls into one of those states. So it's kind of this strange thing where we don't know where it is. We simply know that it's a probabilistic wave over a series of probabilities. And this was something that really bothered Einstein. He really struggled with it and tried to disprove this, but all the evidence that we have kind of shows the opposite. So that's kind of the first principle of quantum mechanics, and I want you to keep that in mind as we proceed throughout the talk. The second principle, which is actually even more fascinating, is something called entanglement. And entanglement occurs when you kind of emit two quantum particles that are connected in some strange way, such that if you measure the state of one particle, the other particle will instantaneously collapse into the exact same state. Okay, so think about this. For example, one of the characteristics of quantum particles is their spin. You'll learn this in one of your courses. Is it clockwise or counterclockwise? And again, we don't know a spin unless we actually measure it. Well, what they have shown is that if you have two quantum particles that are entangled, the moment you measure the spin of one particle, and let's say it chooses to be clockwise, if it's entangled with another particle, that other particle will immediately and instantaneously collapse into that state. And they've done this over various distances. So they've done it, I believe, up to 11 kilometers now, such that if we measure one particle, the other will instantaneously collapse into that state. That reality, that quantum entanglement, seems to contradict another very important law of physics. Okay, think about this again. Let's say I have two particles that are separated by 10 kilometers. I measure one, and instantaneously the other collapses. What principle of physics would that seem to violate? Those of you that have studied physics at the higher levels. Yeah?
The speed of light.
The speed of light, what do you mean?
So they're switching instantaneously over a very large distance.
Yeah.
Traditionally, we would think that it's impossible to have information transfer like that faster than the speed of light.
Exactly. And what physical theory says that nothing in the universe can travel faster than the speed of light? What theory is it? Does anybody know? Back there? The theory of relativity. Which theory of relativity? Yeah? The special theory of relativity, exactly. So we seem to have a contradiction with respect to quantum mechanics. We're saying that these things happen instantaneously, and they have. This has been confirmed by experiment, but nothing travels faster than the speed of light according to special relativity. So does anybody know how we get out of this apparent contradiction? It seems like we've disproved special relativity, but you guys certainly would have heard about it before me speaking to you, right? The argument, which many physicists believe is somewhat of a weak argument, goes like this. If you actually read the special theory of relativity, what it says is that information cannot travel faster than the speed of light through matter or what have you. And what is argued here is that information is not traveling, because you cannot transmit information because the particle is choosing to collapse randomly into one of its states. And so information is not traveling faster than the speed of light. And as one author wrote, it's like special relativity, survives by the skin of its teeth. But this still makes physicists uneasy, because something, whatever it is occurring apparently instantaneously over large distances. And if you're ever interested in the theories around this, this is when you get into like superstring theory and things kind of underneath the quantum world, where they envision 10 dimensions, and there's actually another dimension that connects them and so forth. Okay, so the important point for our purposes for quantum computing is that entanglement happens. Is that if two quantum particles are entangled together, the minute I measure one, the other will collapse almost, or instantaneously, not almost. Okay, now let's talk about something called quantum bits. So with regular computers, you guys are used to bits that are either 1 or 0, discrete and kind of absolute. What's interesting is that in the quantum world, we can take advantage of this idea of superposition. We can take advantage of something being in a, fluid or nebulous state, where a quantum bit now can actually represent probabilistically both states at once. Okay? Let's take a look at the mathematics behind this, because it's kind of interesting. So the first thing to note about quantum computing is that when we write states, we use an antiquated kind of syntax called Dirac notation. Okay, this comes from a physicist who kind of did a lot of theory in this area. And you can see here, first of all, that when a quantum bit is in 0 or 1, we say it is in approximately 0 or 1. That is, with high probability, it is going to be either 1 or 0. Now, you may find this disturbing, because you guys are used to concrete bits, right? When you write in whatever language you write, Java or C#, and you say int x equals 0, you expect it to be 0. The first thing to actually note, and you'll learn this in 231, is that a transistor, when it switches to on and off, actually is also doing the same thing. Okay, it is switching with a high probability of voltage, such that it, we can say with 1 to the 7 billionth degree that it is probably or 1 or 0. Okay, so realistically, you actually have this as well. Now, here's the fascinating thing about quantum computing. This is where we depart the classical world and we get into quantum weirdness. We can say that a quantum bit, in addition to being a 1 or a 0, is in fact a superposition of 1 and 0 at the same time. And in front of the 1 or 0, we attach probability amplitudes, as we call them, alpha and beta. Okay, and we say with probability x, you can be a 1, and with probability y, you can be a 0. Now, if we were dealing with the classical world, what would you expect the relationship between alpha and beta to be? What would they kind of have to satisfy to make probabilistic sense? Yeah. Alpha plus beta would have to equal 1. And what kind of numbers would alpha and beta be? Decimal real numbers, right? So you'd expect real numbers that add up to 1. Right? If you think about the chance of raining, let's say we drove up here, it was raining like crazy, we were listening to the radio, they said it's a 60% chance of rain, therefore there's a 40% chance that it won't rain. Here's the strange thing about quantum mechanics. Alpha and beta do not do what you expect. Okay? They don't add up to 1. In fact, their squares must add up to 1. So we are dealing in the quantum world with what we call a two-norm system, or a two-dimensional system, to represent probabilities. Now you may think this is not really that much of a distinction, because they do have to add up to 1. But the minute I square them, what does this say about what alpha and beta could be? They could be real numbers, correct? But they could also be other kinds of numbers. What kind of numbers? What's that?
Rational.
Rational. Well, yeah, but real numbers can also be rational, right?
Complex.
Complex numbers and negative numbers. Okay, so this is strange because you wouldn't expect to hear a negative probability, right? We'll get to that in a second. But here is how to think of the quantum world versus the classical world. So classical world, 1 or 0 with, you know, definitive certainty. In the quantum world, yes, I can have 1 or 0, but I can also have bits that are in superposition, meaning they could be a 1 or a 0, we just don't know until we measure it. Now let's talk about what I just mentioned, and that is negative and imaginary probabilities. This really seems bizarre, and it took me a long time to really appreciate what they were talking about here. So we understand probabilities in the real world, right? But imagine a negative probability. How would that make sense? It doesn't make sense, right? Like imagine the probability of, you know, asking the crush that you have out and they give you a 0% chance that you're going to go out with them, okay? But then you ask them and they say there's a negative 20% chance they'll go with you. Talk about like adding insult to injury, right? So how can you have a negative probability? Does anyone want to take a stab at it? A negative probability really seems bizarre. No? So the best analogy I could come up with, real world analogy, was this, and it just recently happened, so bear with me. So my sister, who's younger than me, was planning a trip to Vegas with her girlfriends, or one girlfriend in particular, and they wanted to see Britney Spears. You guys know who Britney Spears is, right? Don't make me go there. I actually saw her. It was really great. So they couldn't come to an arrangement on like where they were staying in Vegas and like the hotel they were staying at and the tickets they would get. So they both decided not to go. But not only that, they both decided that if they weren't going to go, the other person wasn't going to go. So there was a 0% chance that my sister was now going to go to Vegas. But by her not going, it also gave a 0% chance that her friend wouldn't go. One way to think about this is that a negative probability in the quantum world, okay, not only says that the particle will not be there, but it will dissuade or discourage other particles in the vicinity from being there as well. Okay, one of the things you guys might have learned is that a particle, and Einstein showed this, is both, at the quantum level, is both a particle and a wave, right? It exhibits wave-like, characteristics. And so waves can destructively interfere with one another. And so negative and complex probabilities in the quantum world are basically describing destructive interference. Okay, they are describing scenarios where not only can a particle not be there, but it will reduce the chance that another particle will be there as well. Okay, we're going to take a look at some quantum algorithms to kind of take this concept a bit further. Now, where things get even more interesting is when you combine multiple qubits together. Right? So consider, for example, a 3-bit qubit register, all in superposition. So I'm saying that one qubit can be in superposition, it can be in 1 or 0, and we don't know which one. If I take 3 qubits in superposition, I'm saying that those 3 qubits can be in any combination of 1 to the power of 2n minus 1, so 1 or 8, with equal probability, right? So there's a 1 over square root 8 chance that any of these, that this 3-bit register can be in, the state of 1 to 8, or sorry, 0 to 7 in this case. Now here's the thing. Again, the minute you try to measure one of the states, it collapses into one of them. So it's all great in saying, hey, this 3-bit qubit register can be 0 to 7, and it can simultaneously be in a state that represents 0 to 7, but the minute I try to measure it, it'll collapse into one value, like 6 or 5 or whatever. So that prompts the question, if in fact the minute you register it, it collapses into a value, what is the point of this in the first place? It's all great in saying it could be any of these things at the same time, but at the minute I measure it, it's going to collapse into one of them. It's just like having a classical register, isn't it? Right? So what is the point?
The point is that you'll get a probability of which one the state will most likely land in, so that when you do the calculation multiple times, you can get an answer.
Okay, so the probability, there's a possibility that it'll collapse with higher probability into something, and maybe that something will tell me what it could be. That's a good one, and we'll see that when we talk about one of the quantum algorithms. Yeah? Okay, anybody else? Here's the strange thing, is that when you perform a calculation with quantum bits in superposition, you can in fact perform the computation on all the values that they hold. And you can manipulate them concurrently and then pick out the answer you want. It's a technique called quantum parallelism. Okay? So in other words, although the minute you measure a state, it collapses into one of those values, when you have quantum bits in superposition, they are representing all the values, and when you manipulate them, you are manipulating all their concurrent values at the same time. Okay? And then when you pick out the one you want, you can do some clever techniques and actually get an answer. So it allows a level of parallelism that we cannot achieve with classical machines. And you'll see this when I talk about some of the algorithms. Okay, just very quickly. We talked about kind of the foundations of computers, right? So storing bits or manipulating bits is one of them. The other thing is, how do you actually have these bits go through some logic, right? So again, I believe in 231 you'll learn about the construction of AND gates and NOT gates and so forth. In the quantum world, we have two types of gates which are kind of primary. The first is called a Hadamard Gate. And a Hadamard Gate basically takes a quantum bit in a position of 1 or 0, and it basically rotates it 45 degrees. Okay, so you can see that if it's a 0, it rotates it such that the probability it's going to be 1 or 0 is exactly in superposition, and if it's a 1, it kind of rotates it again. So there's a half chance it could be in 0, and a half chance it could be in -1. The other gate that we have in the quantum world is something called the Toffoli gate, and a Toffoli gate will basically flip the third bit if and only if the first two bits are 1. The reason I show you these two gates is it was demonstrated formally in 2002 that these are the only gates that you need to construct a formal computer. From these two gates, you can get all the other gates that you guys are familiar with: exclusive OR, AND, NAND, and so forth. Okay? There's also an interesting concept in the quantum world called the no-cloning theorem. And the no-cloning theorem says that if I have a bit in superposition, a qubit in superposition, it is impossible for me to clone that bit and get another copy of it also in this unknown state. Why do you think that would be the case? I have a qubit, it could be in 0, 1, I don't know what it is, and I want to create an exact replica of it, and I want to send them to two locations and measure them, and they're going to collapse in the exact same way. Why can't I do that? Yeah?
To make a copy, you have to observe it.
Exactly, right? To make a copy, I have to observe it, and in the process of observing it, it collapses. Okay, this is an important principle when we talk about things like security and so forth in the quantum world, okay? So the no-cloning theorem is an interesting one. Keep that in mind as we proceed. All right, let's move on now from this theoretical discussion. Let's talk about some quantum algorithms. Okay, first of all, what are quantum algorithms? So in the world of quantum computing, as in the world of theoretical physics, you really have a kind of a division in the community. Not a bad division, just a division in terms of discipline. So in theoretical physics, you basically, or physics, quantum physics or what have you, you have the theorists who basically sit in rooms like this all day and theorize. And they write equations and they come up with theories, and it's purely an intellectual, abstract kind of exploration. Then you have the empiricists, or the practical people, who do the work of building the particle accelerators and building the actual experiments and so forth. The LHC, which is the Hadron Collider, right, in Geneva. Basically, it smashes atoms and electronic particles at almost the speed of light, right? That's the empiricists, but they're trying to confirm what the theorists are saying. In the quantum world, you have the same division. You have people who come up with theoretical constructions which assume that a quantum computer exists. And then you have people that are trying to build a quantum computer. So what we are talking about here are the theorists. These are people who assume a quantum computer exists, and then they ask the question, if it exists, what could we do on it? So keep that in mind. I'm going to show you hypothetical things. This does not mean that we can do them today. This means that when we get to a point where quantum computers exist, these are some of the things that we can execute on them. Okay? So we're going to talk about a few algorithms. Now, before quantum computers were even theoretically possible, again, people were trying to devise, are there things that I could do faster on a quantum computer than on a classical machine? Are there things I could do to take advantage of the unique characteristics of quantum machines and therefore do them faster? And one of the first people to prove this was a guy named Simon, and he came up with an algorithm in 1994. And the algorithm basically says this. It's a very contrived, so kind of fake scenario, but it was one of the first one that demonstrated this was possible. So Simon said, let's say you have a function that takes in a string of n characters and outputs a string of n characters. And you don't have any insight into what that function does. Right? You are simply, it's like a hash kind of function. You are told additionally, though, that for all the distinct, strings that you could give this function, that the function will spit out the same thing for x and y if x and y, when knotted together, produce a secret string s. And so the problem that Simon constructed was write an algorithm to find s. So if you were given this problem in a programming contest, how would you solve it? So f is a black box function. It simply takes a string of n characters, it outputs a string of n characters, and you are told for some two values it's going to output the same thing, if and only if that condition is met. So you have to find s. How would you do it? Yeah?
Try a lot of strings.
Try a lot of strings. Basically, it was shown that on a classical machine, you have to try all the combinations. And so the running time on a classical machine is 2 to the power of n over 2. Simon demonstrated, again, I won't get into the details too much because I actually want to show you another algorithm which is a little more practical, but he nevertheless demonstrated that this could be done on a quantum computer, if one existed, in only n steps. And it was one of the first demonstrations we had that a problem could be faster on a quantum computer than on a classical computer, not because a quantum computer would be computationally faster, but because we could take advantage of superposition and other things. And since then, theorists have also come up with other algorithms. So there's something called recursive Fourier sampling. Okay, in a classical machine, it takes n to the power of log n. It's only n steps in a quantum computer. There's something called Grover's algorithm, which is a search algorithm for an unsorted database. It's 2 to the n for a classical computer. It's half the time in a quantum computer, and so forth. But let me actually get to a very practical problem. Okay, and this was almost a lightning bolt to the quantum computing world when it came out, and that is Shor's algorithm. So Shor was able to demonstrate that you could factor a number in polynomial time using a quantum computer. First of all, why is that problem, the problem of factoring a number, why is it so relevant and practical to the computing industry? Yeah.
RSA.
RSA. What does that mean, RSA? What's RSA? What's RSA?
An encryption algorithm.
An encryption algorithm. Does anybody know what RSA stands for? Yeah, I can never pronounce them either. Yeah, the name of the inventors. And RSA is a public-private key cryptography system that is premised on the difficulty of factoring very large numbers. Okay, so what they do is they pick two prime numbers that are incredibly large. They have about 100 digits. They multiply them together, and that's a public key. And from the public key, you can reverse engineer it and get the private key, but it requires you to factor the number. Okay, does anybody know what is the fastest algorithm for factoring a number on a classical machine? Yeah.
The numeric field sieve.
The number field sieves method. Yeah, correct. And it basically takes O to the 2n over 2, or 3 maybe. Right? So it's an exponential type of algorithm. And that is the basis for RSA. That's why it's so hard to crack, and people are relatively confident that RSA is secure. So Shor was able to show that if we have a quantum computer, we could do this in polynomial time. And his algorithm depends on a few things: modular arithmetic, quantum parallelism, and something called the quantum Fourier Transforms. So I'm going to try to unpack it for you, because tying this all together will kind of show us the power of quantum computing. So the first thing to realize is that Shor leveraged a finding from number theory from the 18th century. Okay, very famous mathematician, Leonhard Euler. He basically said that if you have this function up here, okay, if you take a number and you raise it to a certain power and you modulus it by, another number, that will create a periodic function. And the frequency of that function, so how often it repeats, will actually give you insight into the divisors of the number you're dividing by. So let me actually show you an example, because it can be a little hard to follow. So let's say I choose n equals 15. Those are the two prime numbers I'm choosing, 5 and 3. Right? I multiply them together, I get 15. And then I'm going to choose 7 as the number to which I'm going to modulus by. So you can see here, as I go 7 to the power of 0, 7 to the power of 1, 2, and I modulus by 15, eventually this series will repeat. Okay, in this case, the period is 4. Euler was able to demonstrate that from that frequency alone, we could determine the divisors of n. Okay, there's some mathematical trickery we can do that will do this. So the first question I have for you is, well, doesn't this give us a recipe then for breaking RSA right now? Can't we use this technique, run this algorithm, get the frequency of this function, and break RSA? No, because somebody would have thought of it, right, and already done it. But why? Why can't we do it? Yeah?
I think it has to do with the fact that when you divide by like a really large prime number, then the frequency is also that prime number.
Yeah, right? Because again, in practice, n is so large. So the frequency eventually will come, but you'll have to go through almost the size of the number in order to get the frequency. Right? So this doesn't give us an algorithm for factoring quick. It's just an interesting mathematical technique until Simon was able to apply quantum computing to this. So let's see how we can do quantum computing. So what he basically does is this. He creates an output register, and he basically creates a superposition of all the numbers. So he goes through them in polynomial time and gets a superposition of them. And then he uses something called a quantum Fourier transform. You guys will learn about Fourier transforms in second year, third year? Yeah. Something around that? Okay, Fourier transforms are like signal processing. Okay, there's Fourier transforms, fast Fourier transforms, and now there's quantum Fourier transforms. And he basically uses that to extract the frequency. So let's take a look at this. Let's say again, we have our integer which is 15, right? We're going to pick something that'll hold all these numbers. So we pick a number between n squared and 2n squared, we'll pick 256. Then we pick the integer we're going to divide by. So we'll pick 7. Now here's where, again, we depart the classical world and we enter the quantum world. We have two registers which are entangled. What does that mean? That means if I observe one of the registers, the other register will collapse. Okay? So I have an input register which is 8 qubits because it needs to represent r to minus 1. And an output register that is 4 qubits that's going to basically have the result of the modulus division. I initialize the system. So in the input register, I create an equally weighted superposition of the numbers that it contains, 1 to 256. And in the output register, I initialize it to 0. Now here's the point. As I start running through this algorithm, right, as I start dividing the numbers, the output register rather, will basically contain the results of my division in superposition. Right? So if we go back to the function that I showed you a few slides ago, you can see that when I divide, right, the numbers are going to be 1, 7, 4, 13, and then they're going to repeat. So as I start running this algorithm, I have an input register that is going to be 1, 4, 7, or 13 with equal probability. Now you might think, well, doesn't that right away give me the frequency? If the input register is only going to hold one of those 4 numbers, can I just get the frequency from that fact? But remember, this is the quantum world, so it's holding all 4, but the minute you try to measure it, what happens? It collapses right into one of those values. So here's where the magic happens. I have 2 registers now. I have one that contains an equal superposition of 1 to 256, and one that contains an equal superposition of 1, 4, 7, and whatever it is, 13. I take a measurement of the output register. That's going to cause it to collapse into one of the values. Again, 1, 4, 7, or 13. When I do that, because the registers are entangled, the other register will partially collapse. And it will collapse into all the values that caused that modulus remainder of 1. So in the output register, I'll have 1. In the input register, I'll have an equal probability of all the numbers that caused it to collapse into 1. And then I use a fancy thing called the quantum Fourier transform. That's again based on a Fourier transform, which you guys will eventually learn. And from that, I get the frequency, which is 4. And once I have the frequency, I use a little bit of trickery at the end, and I can factor the number. Okay, and so what Shor showed was a algorithm to factor a number in polynomial time, right? Whereas a classical computer can only do it in exponential time. The challenge practically is that we need a register of hundreds of qubits in order to do this. Okay, and as we'll see, the largest register that's been created practically is about 80 qubits, right? So we're a ways off. But nonetheless, he basically showed that this was an algorithm that could factor in polynomial time, which is quite an achievement. Okay? Now, what this basically shows, what Shor's algorithm shows, is the reality of quantum computing. It kind of crystallizes us very nicely. And it says, a quantum algorithm needs to generate interface patterns in which the computational paths leading to a wrong outcome cancel each other out, while the path leading to the right outcome reinforce each other. Right? So, in order for a quantum computer to do things quickly, the problem that you are trying to solve, whether it's factoring a number or finding an unsorted element in an unsorted database, they need to be able to take advantage of this weirdness that we have with superposition and entanglement. And that's a delicate requirement that you'll only get with a certain class of problems. So what you should take away from this is that with quantum computers, we can do certain things incredibly fast, but only for a certain class of problems. Okay, they will not in and of themselves automatically make every problem that we have in the computing world faster. Okay, it'll apply to a special class of problems, but when it works, it can do things much quicker than we could have on a regular machine. Okay, and that's really the power. Okay, let's go through some last things very quickly. Obviously, the implications for this are security, right? So I mentioned RSA would collapse if we had a working quantum computer. And of course, there's conspiracy theorists who say that the NSA and other intelligence agencies already have quantum computers that can do this. Okay? That said, does anybody know what an alternative to RSA would be? RSA is the most popular public key system that we have today. There are others, though. Does anybody know any other systems that exist? No? One of the most popular alternatives is something called elliptical curve cryptography, ECC. And elliptical curve cryptography gives us roughly the same strength as RSA, even with lower key sizes. Okay, and it's based on the mathematical theory behind elliptical curves. Incidentally, elliptical curves were the centerpiece of one of the most famous mathematical proofs in the last 150 years. Does anybody know what mathematical proof elliptical curves was connected to? It was the most famous unsolved problem in mathematics until it was proven.
Fermat's last theorem.
Fermat's last theorem, correct. Does anybody know who proved Fermat's last theorem?
Sir.
He was knighted. Very good. He was knighted. Sir who? Andrew Wiles is his name. Okay, and he was at Princeton University. He solved it. Well, he announced his proof in 1993. They found a flaw in it. He corrected it in 1994, and it was published in the Annals of Mathematics in 1995. And if you actually go to the DC Library, is it still called the DC Library? You go to the bottom, there's the Annals of Mathematics there. You can pick out the 1995 edition. You'll see his proof, which is about 120 pages. And they say there's a handful of people in the world who would understand it because it's so technical. Okay, does anybody know what the most famous unsolved problem in mathematics is now, given that Fermat's last theorem was solved? Yeah?
P versus NP?
That's a computer science problem. And if you solve that, you'll win $1 million. That's the Clay Millennium Prize. It's something called the Riemann hypothesis, which has to do with complex number analysis. So, given that ECC exists, okay, can we use ECC as an alternative? Well, as you see here, it's been also demonstrated mathematically that ECCs would be susceptible to quantum attack from quantum computers. So they won't work. Okay, probably the most promising area of cryptography we have is something called lattice-based cryptography, which basically has to do with placing points in a Euclidean space and then coming up with problems around those points, like the shortest vector problem and the closest vector problem. Okay, there's a lot of theoretical research in this area now, given that quantum computers might eventually break RSA. Okay, there's also something called quantum key distribution. So you might remember we talked about the no clonable theorem, right? Which says it's impossible to clone something in superposition. that actually creates an interesting possibility to exchange a key between two people without prior knowledge of that person or any requirements. Why? Because if I send something in an unknown state and somebody tries to eavesdrop and intercept it, automatically in the process of measuring it, they'll collapse it. So I'll get it and I'll know it's collapsed, and therefore I know it's been tampered with. Right? So that's an interesting application of the no-clonable theorem. Another one is something called quantum money. And that is because, things in superposition cannot be cloned. Okay, there's been research going into things like, could you actually create a monetary system based on the no-clonable theorem? Kind of as, a successor to Bitcoin. And so there's research going into quantum money as well, which is quite fascinating. And the one you guys will really love is quantum teleportation. Of course, this conjures images of Star Trek and sending people, to other galaxies faster than the speed of light. This is not what quantum teleportation is. Quantum teleportation is the ability to send a bit in superposition to somebody else. And if you think about it for a moment, you would think that would be impossible. Because again, in the process of measuring a bit, we collapse it. It was actually demonstrated, and this was a real surprise when it was demonstrated in 1993 that this was possible. And it basically involves having two bits in superposition, entangled, sending those two bits to two different people, and then having the third bit in an unknown state, and basically performing a calculation on one of the bits, the entangled bits, and getting the difference between those two bits, and then sending that difference through a classical communication channel to another person. And using that information or that difference, they could then construct that unknown state. And here is an example of quantum teleportation. Now, the no-clonable theorem is not contradicted here because the original copy is destroyed. Right? So it's when I want to send an unknown state A between two places, I basically would have B and C. I'd measure the difference between A and B, and I'd send that difference to somebody else, and they would reconstruct the unknown state. So quite interesting. The problem, though, is because I need to send that information or that difference classically over a classical channel, the fastest I could go would be the speed of light. And so this whole idea of teleportation and this being related to quantum computing, unfortunately, does not really make sense or exist. Okay? All right. We've got 2 minutes left. So with 2 minutes, I'm basically going to tell you where we are with quantum computers. That was all theory. Where are we really with quantum computers? Many different techniques are being tried to construct quantum computers right now. And you guys are lucky because you are next to one of the foremost areas of research in the world, the Quantum Computing Center, which is right across campus. There's also the Theoretical Institute for Physics, and they look at some of this stuff. The problem with quantum computers as they exist today is something called decoherence. And what that means is that as you start constructing quantum bits and you start putting them together, those bits get entangled with the outside world unintentionally. And so the minute that happens, your system collapses and your quantum computer becomes useless. So this is the biggest problem that empiricists are really facing right now. And so here's a quick history of where we are with quantum computing. So in 2001, IBM used Shor's algorithm, which I showed you, to factor the number 15. Okay, we've had researchers in 2010 perform calculations with 2 qubits. You can see physicists have got entanglement with 14 qubits. There's a company called D-Wave based in British Columbia, and they have claimed that they have a working quantum computer with 84 qubits. And their claims have been disputed because they haven't really shared a lot of the theory behind what they've done. In 2012, physicists created a working transistor from a single atom. And you can see finally in 2013, we had the coherent superposition of 3 billion qubits for 39 minutes. So clearly things are in their infancy. In 2014, Chinese researchers trained a quantum computer to recognize very rudimentary handwriting. So we are in our infancy, no doubt, with quantum computing, but this is probably like the 1950s with classical computers. You can see marginal progress, and who knows where we'll be in 20 years. Most people think we're probably 20 to 30 years away from practical quantum computers. Could be faster depending on how research goes. But once they come, okay, you can see that the potential for this is quite limitless. Okay, so to wrap it all up then, quantum computers take advantage of quantum mechanics and the unique characteristics of quantum quantum mechanics that we do not get at the classical world, right? Superposition and entanglement. Quantum algorithms can take advantage of those, but only for a small class of problems, such as factoring a number or finding something in an unsorted database. We are at least a decade away, in the opinion of more, people a little bit more than that, from practical quantum computers. But if they exist, and when they exist, it would have profound implications for things like security, RSA, artificial intelligence, and so forth. Okay, and finally, I'm going to end with this little cartoon, which came out a few years ago. And we are exactly at 10:20. So thank you guys, and I'll stick around if you have any questions.